well. You have one of the, for sure, the best guy in Denmark for Leap. I don't know about globally, but for sure you have the best guy in Denmark. So to teach you Leap, and I don't mean Francesco yet.
So I know the timelines. I'm not the best. I apologize, especially for the last lesson. Doing optimization Leap took a lot longer to actually make the lesson than I expected. It took a bit under 7 hours to make that lesson, which I thought would be about half. So optimization especially is hard. That's also a decent lesson here. As a note, by the way, I'm recording this, so Stefan, you can also have it afterwards, and I'll put it on YouTube as well, unlisted.
Actually, I'm just going to let you give the lecture, you and Francesco. I'm just going to turn off.
Before I go, I have one question for you, actually. I tried calling you earlier. In terms of diplomas, any plans on that?
Sorry, can you say again? Diplomas?
Mm-hmm.
What about that?
Yes, no, will that be? Should I contribute? Should we do something? And that may be also a question for everybody else. Would you actually like diplomas at the end of the course?
Sorry, you mean what is diplomas? Sorry.
A certificate, yeah.
Oh, okay.
Yeah, you mean we for sure will give them diplomas for the course, but you mean Leap diplomas?
No, not necessarily. I just need to know if I need to do something with the diplomas, but we'll take that afterwards. I just needed to know if we are doing it or not.
Yes, I think that for sure they should have diplomas. I think we discussed it a long time ago. For sure they should have diplomas, and I think even better would be to have diplomas with Leap. Separate diplomas with they received so many hours of training in Leap.
Yeah.
So it would be for two, one for the whole course, one for Leap.
Yes, I'm going to do something slightly mean, and I'm going to make it a requirement to solve exercises I'm going to give you tomorrow to get a diploma. But we'll get to that in a second.
Maybe just one thing, even though you're recording, it's not regarding this course. Did you see my email about the licenses for the other course? So what is your opinion? What should we do that? We can take it afterwards.
No, yeah, right. We'll take that afterwards. Basically, that has something to do with you for everybody else, but that's actually not quite my table because I'm not involved in that. But it's something that you will have to talk to Charlie about. That's
we can. Do we say we talk at 1? We talk at 1.
I might have a meeting there. I'll text you afterwards or email you afterwards when I have time.
You email me when you have time to talk, and then we take it.
Sure. Yeah.
Francesco, Gregas, students, have a nice day, have a nice lecture, and I see you later.
You too.
Bye, Stefan. Thank you.
Bye.
Bye.
Thank you.
All right. Now the grown-ups has left the building.
Yes. Sorry, Mr. Larsen. Did you send any video for today's lecture?
I sent a video for lesson 4. It came out late. It's okay if you haven't watched it. I will go through some of it. It's about optimization, by far the most of it. It is on YouTube. And I sent out an email yesterday evening about it, yesterday evening Danish time about it. But it is on YouTube, and I will just give you guys the link here as well, so you can watch it afterwards if you want. Just give me 2 seconds.
I didn't find any email, and I checked your video also, YouTube channel, but I can't find the video.
Yeah, my right now it's not a public yet. Any of the videos I have given you because it needs to be put somewhere else afterwards.
Okay, please send us a link.
Yes. So here are lesson. So that is in the chat right now.
Okay.
It's about 1 hour video, but as someone else said, I said it was Sanwabo, it took him a while to get through because it's pretty complex, and it is pretty complex. It's about optimization. So I realized that the videos have been out a little late. I apologize for that, and it takes longer to do courses than I kind of predicted. That's also why I haven't done exercises, because I was afraid I was going to have things out too late, which I was right. But speaking of that, I'm just going to show my screen in a second. Really quick presenting. Things please continue. You guys should see a PowerPoint slide right now, right?
Yes.
Good. Okay, so I want to talk to you about exercises because some of you have been requesting it, and I think it's a good idea. I have just timing has been a little bit difficult, to be quite honest. But so we're gonna do it from tomorrow. The first thing is I am going to make one video more about these exercises and put in YouTube and send you all an email. And I will try to do that today. It shouldn't take too long, but I need also to make some of the things in the exercises I haven't done yet. So it might take a little while. Why it's change automatically? Not meant to. So that means that we are going to have 3 exercises. We are going to answer them in a survey, and the people who have already answered the first exercise, don't worry, I will look at that too this evening as well, and I will give you personal feedback on that. And I will put some start files on the SharePoint, and it will be a build on top but independent exercises, meaning that I will give you something to do in the first exercise, and then the second exercise will kind of start at a similar point to what you did in exercise 1, but the numbers will be different. That means you cannot see the results to exercise 1 from exercise 2. It also means that if you made a mistake in exercise 1, it won't impact exercise 2 answering. Just so we have that quite easy. I will put that up before tomorrow evening at 6 o'clock. I'm going to give myself a little bit of time, even though I'm going to start just after this lecture and work on it most of the day, because quite frankly, lesson 4 took way longer than expected, and I want to have optimization in the exercises as well. So that's also going to take a long time. These exercises will include working with data in demand, transformation, and resources, meaning all 3 main branches. It will involve making branches, making methods in the branches, and also inputting data. It will also involve some kind of importing and exporting data through Excel. So you should have Excel on your computers, right? I assume most of you do, at least, or all of you do. So it will involve that. That's from lesson 3, I think, yes. And then it will also, probably only exercise 3 will require optimization as well, which also means you have to have Nemo installed, and Nemo is already on the SharePoint. And in the beginning of of the video for lesson 4.2, I have already specified how you can check if you have Nemo installed, because it can tell you in Leap in the About section. And then you should be able to run that. The way it's going to work is I'm going to use this PowerPoint I'm showing right now, and I'm going to build on it. So I also can tell you on video, just like the lectures, something about the exercises, because I have found previously when I write things down in a Word document, it's very difficult to have like context and to tell things in the right order, because it gets all a little bit jumbled. So I'm going to do it with a video that I will be putting on YouTube before tomorrow evening at 6 o'clock. I will make the exercises so it would be solvable. If you are perfect at Leap, you could solve them within an hour. So hopefully you can solve them within 3, 4, 5 hours, including calculation for optimization and so on. So I will make them pretty specific to what you have to do. And in terms of if you want a certificate for the Leap course or the Leap part of this energy planning course, I will require completion for having the diploma or the certificate. but I will not write how many you got right, because that also depends on a lot on how well I can explain the exercises, and explaining exercise in Leap is generally difficult because there's so many places you can put data and so on. So I think we should be a little bit large with that. You have to deliver that by the end of 18th of October, Central European time, and that's the reason I want that is at the 18th of October, I'm going to put all the result files up. So similar Leap files, but just where I have solved the exercises. And then you will have 2 days to look at it before your license expires. So be aware of that. So from tomorrow evening at the latest to the 18th, that will give you 3 days to make the exercises. And I will estimate it will take 3 to 4 hours. It will be a good idea to look maybe at some of these lesson 1, lesson 3, and lesson 4.2 especially, because I think that's the most important things in the different lessons before I will send out these exercises, so you're a little prepared. And then you have to answer that in the survey, and the link to the survey I will put in also in the email and also on SharePoint, so you can always find it. That was basically all I had with that. Does that sound okay? Oh, do we do the exercise in group, Zanwabo? I think you should deliver it personally, but if you solve it in a group, it's fine. I might even put in a comment section where I can say like, hey, I solved this with the other people, just so I know what it is. But I don't think you have to solve them alone, but you have to answer your own survey. Yes. Any comments or questions to that? No? Are there any comments and questions to lesson 4? If you have seen it.
Hello. Can you hear me?
Yes, I can hear you,
Okay.
Sanya.
I have a personal computer and also computer in the server of the ministry. So I tried to install the software on this work computer, but I couldn't get Nemo installed somehow. Then just they connected remotely and installed those with administrator rights.
Right.
But now in the help section, it says Nemo yes, and it shows the path for Julia, but still when I'm launching the Leap, it gives some warnings regarding those not CBC, but some other solvers. It says it couldn't, something like it couldn't locate it. And on my personal computer, I have problems. It works perfectly because when I installed Leap, Nemo and Julia came automatically. But for yearly shapes, it just freezes when I opened and try to select another year shape group. It just doesn't respond.
In terms of your issue with yearly shapes, uninstall Leap and install it again. I do that honestly about 3 times a year. Leap is a little bit weird. It's a small team and a small software. And Francesco, I can tell you, uninstalled and installed Leap yesterday because of similar issues.
Okay.
Quite frankly, I can't do anything about that. I'm just a user in that regard, just like you. Okay. And I hate when that happens. In terms of your admin rights, that's also a problem. Actually, I'm doing these lessons from my personal computer as well, because our work computers is also impacted by lack of admin rights, and that creates a host of problems as a general thing. So I have kind of given up on my work computer, but that is between you and your IT department, and it's not something I have any right to solve. But in terms of the if it gives you a warning, you may have chosen a the Mosaic maybe solver, and you don't actually have that. Maybe it's also Cplex if there's some kind of Cplex in the model. That's a commercial solver that costs a bunch of money, and it probably means that somewhere in your transformation sector, it has said that you would like to solve, say yes to solve on using Cplex or Mosaic, which just means you kind of have to go into transformation sector, I can show you, and
Yes.
just choose another solver.
Yeah, I just did that. Actually, it was Cplex, and I have Cplex on my computer, but somehow while installation, it says it cannot find it, so it doesn't see Cplex as well. And in settings, in optimization tab, normally in my other computer for installed optimizing frameworks, it says Moses and also Nemo, but here, although it says in the help section, there is Nemo, it doesn't say in the optimization tab. So just if you have any hint or something, this is why I asked. If you don't know, it's okay.
Use CBC. I don't have Cplex on this computer, and also my version of Leap doesn't actually show Cplex, and I don't quite know why, because it used to be the main solver, faster solver. But I know from the people who made Leap, they are unhappy with the pricing of Cplex because it's very expensive. So they might have just gone over to CBC instead. So I highly recommend choosing CBC as a solver. And I will also say that in the exercise, I had pretty good luck with that, even though I only had Nemo installed, because it's open source and it's quite fast. Did that answer it?
Well, I cannot select any of them since there
really?
In the optimization part, it doesn't say there is Nemo.
Oh, okay, sorry, I misunderstood your question for a second. I just need to see something in. So in the optimization part, you are in, excuse me, I'm just going to show my screen in a second. Share screen. So what you're talking about is on, do you see Leap on my share screen? Good. So what you're talking about is, for instance, in electricity generation, optimize, right now it's 0 because it's just a small model. And then here you don't see this.
No, I just see no, yes, but yeah, the same. And yeah, that one, not Nemo's.
Okay, can you go to help about Leap and just to check if Nemo says yes?
Yes, I checked that.
Okay.
But somehow.
It's one of those things. It should be there, but I can't tell you why. It's software. Try uninstalling, installing Nemo again. If you accidentally, I have actually no idea. I haven't run into that. I was afraid that would happen.
Yeah, I just don't want to steal time from our training. Maybe.
I think for now it's okay. It should be said that I cannot. We will not run too much stuff in this training about optimization because it takes too much time to actually run the optimization to really show you anything that's not a video, because I had to cut a lot. Some of these optimizations that I did when I did it with multiple scenarios to get the results that I showed in the lesson, or showed in the lesson 4, they took about half an hour. And we're not going to sit here for half an hour waiting for my computer to finish the optimization of a model. So it's so I cannot show you the optimization. It's because it takes so long. In terms of, again, Osmosis Nemo, try uninstalling Nemo and installing it again while you have Leap closed. I think you have to do that, or else reinstall Leap. It's usually the thing that makes sense if it has issues. It might be because if you have Cplex on it, it might be try to default to something else. But I honestly don't know, because I haven't had any issues. Otherwise, I can give you a nice little email to the Leap team, and they can help you. Because all software issues is it's outside what I can do, because I don't have rights to that.
Okay, thank you.
Are there any?
Larsen?
Yes.
Okay, thank you. I tried to analyze the optimization model you sent us, time slice demo.
Mhm.
And I face also the same problem. There is no Cplex, but I changed the solver with JLPK. It works. So
Yeah.
is there any problem to solve with this JLPK or the same?
No, it's just slow. So the here you have the old standard optimized capacity. Is that the one you're using? The yes. Okay, so if you're just using osmosis, which is these ones up here with DLPK, one, it's quite slow. Two, it cannot do storage. That's the big one. If you're using NEMO framework and DLPK, it can also do storage just fine. It is just quite slow. So if you can use the NEMO framework and CVC, it gives the same results as DLPK, but it is just twice as fast. In my experience, anyway, about twice as fast.
Yeah, I tried to solve it. It already solved, but as you said, it took lots of time.
Yeah.
And make my computer also busy.
Yeah.
And also, I am on Leap now, and the results of optimization are open in my side. And if you want to elaborate something about analyzing the results, I can share my window, and you can show us how to analyze the results, because I didn't understand most of the things there. I know that the result is came, but I can't analyze the results and what to see on which point to focus. I didn't understand well.
Okay. So I also have. Let me just check something here. Okay. I just need to see here, power generation, time slices. So you're probably looking at something like this, right? Like my power generation.
Yeah.
I also have mine.
There are, Sure.
Okay. So I thought I'd just share mine, because then I can more or less control it. So what is I have mine solved as well. That's why it didn't take any time to solve on my computer. Otherwise, this with these scenarios has taken about a half an hour on my computer, just so you realize. So what we have here is if I go back to my analysis, and I have to be careful not changing anything, because then I have to solve. If I go into general, into my time slices, you can see you can see this window with time slices, right?
Yes.
Okay. So I have 24 hours for spring. These are the first 24 hours. Oh, sorry. I have 24 hours for spring. Then I have 24 hours for winter, and 24 hours for summer, and 24 hours for fall. So that gives me all in all 170 something. It said 96 time slices. Okay, and when I go into my result, and then also in general, in my yearly shapes, I have a bunch of yearly shapes that are for my different places in my demand. In this case, I think I've put that on in this calculation. So I have a special yearly shape for air conditioning that fits with the same hours. So these are the same spring, summer, fall, and winter hours. So 24 hours for each for my different main consumption. So air conditioning, heating, lighting, refrigerators, and so on, including some EV charging, and some water heating and so on for all my electric. I also have it for solar, which is a production. So I have all these different shapes. So if I go back into my results, here, what basically is happening now, I'm taking it adds up all these different the different yearly shape times my individual demand in my different sectors, like for air, for refrigerators, for air conditioning, so on, and then it finds out how much is that every single of these single one of these hours in my what do you call that, in how much demand is there, or how much production do I have to make for each one of these hours in my yearly shapes in my time slices. So that's what you see down here. You can see this is spring. Some of these are hour 8, but these are in between, and then summer, fall, winter. So here there are 96 blocks of hours. And you can see they're really divided. This is where we differ between spring and summer, and this is where we differ between summer and fall, and so on. You can see these are a little weird. They cut a little differently. So what is really happening is, like, this is the demand, or this is the production needed, including losses, from the electricity generation for each hour. We follow that here in the top line. Then for each of these hours, we can say some of it is produced by coal, some of it is produced by hydro here, some of it is produced by natural gas, and some of it is produced by nuclear, and some of it is produced by, in this case, wind, and also here solar. So that's what we show here. So you can see that this part here, by this until this cut, this is our normal spring day, the way that we have defined it in our time slice, and this is our normal summer day, and this is our normal fall day, and this is our normal winter day. And this is how we are producing power on each of these hours in that day. So that's actually what we show. And then we can change the year down here. So this is in 2040, and we can see if I put it back to 2019, and then maybe you can see this. We can kind of make it play how the electricity demand grows, and then how we fulfill that over time with our different production units. Does that make sense to everybody?
Yes, yes.
Okay, so that's how what we calculate, and it says, okay, so it knows that this is a normal day, and then it can multiply that day with all the spring days. So it says, like, every summer day looks like this, every spring day looks like this, and every fall day looks like this, and so on for this year in 2040. So what it can do with that is, like, okay, now we find out, with that we can find out how much power we need for a year, and also how we're going to produce that power on a yearly basis. So that's basically what we found. So what is it optimizer says, like, this is the best way of doing it under these conditions, prices, and so on we defined. If we go into different scenarios, so here we have storage and
Sorry,
policies. Yes.
Sorry, just a quick one. I mean, I'm in a utility, so I think it's interesting to see results like this on an hourly basis for the different seasons. But where do I check if, for example, I have enough reserves for the day or for the hour, for example?
Ooh, reserves.
Or is there somewhere where maybe in LEAP one can cater for reserves, so to speak, just to make sure that you have
Yes. So LEAP in the transformation, in the analysis here, now we take the one that we optimized. This is the electricity generation. We have something called here, where if you just click on the electricity generation itself, where you also have the optimize function, optimize tab. You also have planning reserve margin. There you can actually set a number, saying this is the number of capacity I want in reserve, and LEAP always adhere to that. So at every single point with our production, we always have over-invested 30% in terms of margin in the cheapest way with a dispatchable unit that complies with that. So we always have reserve margin. That's something you can set in LEAP. So it will do that, and you can tell here in results, not on an hourly basis, because it always has 30% compared to peak. But we can see here that how much capacity, how much reserve margin do we have in this case in percent, because we are here, I think we are increasing because we also have a lot of renewables. So we have a lot of reserve margins, general reserve margins. Apparently we also have that in baseline. I haven't really played much with reserve margins, so I will look into it, and then I'll probably speak about it in maybe the exercise video. But we will always have reserve margin because we define Leap to always run with a reserve margin. But to have true reserve margin hour by hour, you actually kind of have to have a perfect resolution. And that's too much for Leap. I mean, that's 8,760 hours you have to run, especially if you are considering hydro. And that's one of the most difficult challenges you have in terms of optimization models. That is a reserve margin for hydro. And that is too much for Leap and too much for a personal PC in general to compute.
Okay, now I understand. So is there, so when you're showing it this is the reserve margin on an hour by hour, can you show what the annual peak load is, for example, from 2019 to 2040, say, and then show how much installed capacity you have for each year, for example? I think
Yes.
it will be interesting to see given the installed base here.
Yeah, exactly. So for instance, here we have I'm just going to go back to the energy generation slide once more. Why are we only in that? Because we're in the wrong place. Like this. So this is the one we were referring. This is power generation on all time slices down here.
Sorry, Mr. Larsen. Sorry. By the way, what are the what are the levels? You increase, decrease, the result will. What to indicate you vary the levels? To add additional parameters or?
The levels here.
Yeah, levels on the top. You made it 2 now. Okay. When you try to show us this thing.
Oh, there are levels here. Oh,
yeah.
okay. Yeah. Okay. So that's that just means that now that I'm here in electricity generation, you can see this is bold. When I'm saying if I'm in level 0, that means I'm only looking at this. If I go level 1, I go 1 down, so I can look at all the folders that are below that. In this case, it's just 1. And if I go 2, I go 2 folders down. So now I get all these. So this is 0, 1, 2 compared to where I am, which is here. If I were to do something in demand, I can say households, and level 1 would just be households. So I can only see results for just households. And level 1 is the one below. So now I see air conditioning, space heating, lighting, and so on. And if I go 2, I see a bunch of technologies in this case. So that's my way of viewing results. Yes.
Okay, I got it.
Right. But that was the generation thing. So here in transformation, I can see capacity added. I can both see my capacity. So this is on a year. So this is all years. I can't see it by hour because that's just the same as in electricity generation models. But this is the capacity of electricity producing units I have in my entire system. So you can see wind grows quite a lot. Solar grows a bit. Gas grows a lot in the baseline. And I can choose between different scenarios. So if I have emission constraints, I have more wind and less gas. And if I put externalities on, I will have even more hydro and energy storage and less gas because I'm putting cost on this. So this is my total capacity. What's more interesting even than that, you see also we have a really growing system in this case. So we start very low. So this is my original capacity. If I go here in transformation as well, I can say capacity added. And you can see 2039 was a really big investment year for this policy with externalities. We invested in a lot of gas and in a lot of wind for some reason. The model decided to do that. So this is the capacity that I add to my system in this throughout the years. And then 19, that's since it's our base year, it doesn't show that because we defined that specifically. There's no investments there. So these are all the investments, so to speak, are capacity additions. I can also show, since I have defined my lifetime for all of my units, I can say that actually this might also be a retirement. That might do it. We can check that here. So you can say it's probably retirement. So I didn't retire any units, but here I retired a bunch of nuclear and a bunch of coal. And this means that, oh, now these have gotten too old, so I'm going to skip having my nuclear power plant and my coal plant. And that's also why we added a bunch of capacity, because now we had to invest in something else to make up for this lack of new nuclear, because it didn't set like nuclear doesn't make sense anymore. It's too old. We retire it and we don't reinvest. So we invest in something else that's better or cheaper. So that we do all that here in transformation.
Yeah, thanks, Gregers. That's very interesting to see. So when you retire the nuclear and the coal, and you are replacing it, like you're saying, from 2030 with a lot of wind and gas and a bit of storage. But then obviously there's issues like inertia, for example, that goes with your wind and with your coal and nuclear that you're not necessarily getting from the wind.
And you can
maybe
see, it actually looks at that also on an hourly basis, and that's why you can see we add a bunch of capacity on storage. This is a little more expensive, but that's probably why we add the storage. That's because of solar and wind inertia. So that's to solve that basically. And if you see that in this scenario on the electricity generation, power generation, I have to find it. There we go. And instead of, so this is the generation I did per year, but the more interesting is doing it on hourly basis. And in 2040, and you can see here, so we are charging quite a lot of hours with on our battery basically. So especially here where we have low demand, the gray line, I don't know if you can tell that, it's difficult to see over Zoom, but that's our actual demand. This gray line shows up when you also have things in minus. So here you can see our demand is lesser than our production, and that goes into charging our batteries. So that's what these mean. And that's to solve for the inertia or solve the intermittency for our solar and for our wind. So that's what that's actually kind of what it does here. It is a little simplified with wind. I am not quite sure how to deal with that, because if I put a yearly time on it, it would also be fixed like solar, and I don't want to do that either. So I'm thinking about if I can do a randomization on this, but I haven't actually tried. It should also be said that in terms of investing in capacity and retiring capacity, I haven't done anything. This is the computer who decides, and that's the beauty of optimization, of course. So so this is all a decision that's just based on our prices and on our boundary conditions.
Is my observation right? Because it means like for some hours, the supply is quite tight versus demand.
Oh no, that's on purpose, because the supply generally just follows demand. So we're saying we are doing everything that we can do to just fulfill the demand with our supply. But where that doesn't make sense, where we, for instance, have a bunch of sun capacity, then we use that to charge our storage, and then we can undersupply here. So in this peak, we actually don't supply enough, but we have our storage to make up for that, which we charge during the last hours. So that's what it says here. So it is meant to follow as tightly as possible, and everywhere it doesn't actually follow, that means you're either that you are basically either exporting, or that you are what do you call that, charging your storage. We don't have any export pricing or export benefit in this model. Otherwise, it might also choose to do exporting if it price-wise makes sense. But in this model, it's just zero to make things a little more simple.
Okay, no, thanks. And then lastly from me, I think you're showing, so how would the production look like in terms of either gigawatt hours or megawatt hours versus the load also for the
So per
different
year,
generators?
you mean?
Yeah, it could be per year. Any resolution that is easier to look at is fine.
Boom, boom, boom. So we can say, so here we have a quite a different number of things we can look at. So here, outputs by feedstock fuel. This is for our electricity generation. Here we can see, can you do that? No? That's actually cool. So this is our yearly, so this is just for all years. So this is our yearly feedstock fuel use. Sorry, that's outputs. I need to inputs. That's with losses. I need inputs. There you go. So here I am here in my inputs. This is how much nuclear, how much natural gas, and how much hydro energy, and how much coal I have been using on a yearly basis. So that's one way of doing it. That's the main way of looking at how much fuel you're using. If you want to look at the technologies, where is it? Yeah, it's also here in power generation. Instead of looking at, here we look at all years instead of all time slices, then we see how much we produce from the different, what do you call that? For the different, different technologies. So this is how, this is our yearly. And if you look at tables, you get a specific answer to that.
Yeah, if you go back to this chart here, I thought I would see, because I saw a decommissioning of nuclear and coal. But if I'm looking at the nuclear tab only, I'm not actually quite seeing the decommissioning kick in there.
That is a good point. I need to check something. Did it actually? Yeah, actually, it might be. That's a good question. I didn't notice that. I just need to see something. Because it might be that we are retiring some nuclear, but not all. Because this is 6 gigawatts, I guess, 6 gigawatts worth of nuclear. We might actually have more. So I just gotta check in.
Is it cumulative? It's not 6 gigawatts per year, right? It's just 6
it's
gigawatts.
Just once we retire, like, so that's a retire what we have done. Yeah, it shows up a little weird, I know, but you can actually see here, even in this scenario, we actually still have some capacity of nuclear left. So that means we have in real life, and we can see how it was defined in the analysis. We probably have some. It's in here somewhere. Just give me a second. Maybe it's the optimize. I wonder if that did it. Because it, I don't know if it's that made the decision or if it's our decision. I don't remember where you see that. It's in here somewhere. But where you can see that the here we should be able to see some whether it's just because it got old or it got too expensive, and then the model decided that to cut one of our some of our nuclear capacity. So it can decide to do that, but that was a model decision. It should be lifetime somewhere. I can't find it. Maybe it's just because it's optimized. It won't let me do that. Good question.
Okay.
But I think I think it's just in this case, it's the model that decides that we have too much nuclear in the system. Oh no, I know where I can find it. My bad. It's because I'm in the wrong scenario. Current counts, nuclear, and then that's the thing about being in the scenarios. So we probably have some. It's only so sure so on. So this is not a forced decision or forced retirement. This is a model decision to retire a bunch of the nuclear capacity. Of course, the problem with LEAP is
it's it's not a case like Germany where it's a forced retirement.
No, it's not in this case, apparently. You can also input that just putting that into your lifetime, and there's also a place where you can put in a specific retirement year, or say that the capacity goes to 0 after a certain number of years. That's also a way to do that. Just saying after a certain, maybe that's also there.
Okay.
Actually, I gotta admit, I didn't look too closely into the different.
No, it's fine. I think it's fine. But and then for this system here, so there's no potential for, there's no fuel switching that took place. If there were, where would you see it? Like
Fuel switching inside of a technology, or what do you mean?
or generally speaking, where, for example, let's say for space heating, you were moving from one fuel to another fuel. In
Right.
other words, what I'm trying to say is like I want to see if there's, because LEAP is an energy model,
Yeah.
so I want to see the interdependencies between the different primary fuels, where for example, you could use gas directly for space heating and cooking, but on the other hand, you could also transform it in a power station, for electrical purpose, that type of a thing.
Yeah.
I don't know if you get the gist of my question.
Yes, I do. So for one, the optimization does only occur on transformation sectors in LEAP. So it doesn't optimize your demand. That's pretty important. So right now we're only looking at the optimization in transformation, but something like space heating is something you have to define yourself, and then that's why you use a different scenario. So for instance, here we have quite a lot of gas and a little bit of wood, no propane, and no heat pumps. If we do that with externalities, we have a little bit of heat pumps here. So that's not something that's been optimized. That's something that you can choose, and then you can test that with an optimization. But what you're asking is a little bit like, where does it make the most sense to use our limited resource of gas?
Yes,
more or less, right?
That's correct. Yeah, that's
so
correct.
What I would do, I would set up 2 scenarios. One where we use it maybe mostly on the demand side, and one where we use it mostly in the transformation side. Then I would set my primary fuels reserves for primary fuels, for instance, in this case, natural gas, and I would set that to be. I would set that to be somewhat limited. I mean, have an end reserve so we can remove the reserves. And then you will see when you would start. For one, you would see when you start importing quite a lot. So that meant you more or less spent too much, I guess. And then you can also then, if you put your cost on both your demand side and your transformation side, you can then see the social cost under social cost, and then you can compare. Let's say cumulative values compared to different, I guess I avoided actually, baseline scenario, and I have to go and do that for the entire model. So you can see here, okay, this looked really weird. But what happens here is that in this case, in scenarios, this means that the scenario of, how is it, when it's minus, it is meaning that we don't avoid. Okay, so in this case, our policy with externality scenarios is more expensive from the years 2020 to 2027, and then it shifts and begins saving money. And that means if you take cumulative values, and we have to do comparison again to baseline. Sometimes it just won't let me. So it won't let me do that for some reason. We can also just say difference to baseline in cumulative values. No, come on. Yes. So here, this is our costs. So you can see the costs are going upwards above our, and also where the costs are in our social scenario policies with externalities, and then it shifts and becomes cheaper, and the cost becomes cheaper than the baseline scenario. So that's something you would be able to see there. And if you price your import of gas and export of gas and these kind of things, you will also see that reflected in this social cost, because importing is expensive in terms of social costs. So that's a way of testing that. But you cannot just do that with optimization, because Leap won't let you do that. A model like Times would actually let you do that because it can optimize demand side. But in Leap, you would have to set up 2 scenarios, run them with optimization, and then compare them.
Okay, I understand.
Is the yellow one the baseline scenario, Mr. Larsen? The
Sorry,
cost of is the yellow one. The yellow one is the cost of
no,
the
so
baseline
this
scenario.
no, so this is not the. So these are just different processes. So the yellow one in this case is electricity generation, and the brown here is vehicles. So what it actually says here in the gray line, if you can see that, that's the total cost difference between the 2 scenarios. So what I just did is I took my total cost for the my policy with externality scenario, and then I said, like, hey, minus that with the baseline. Where do we spend more money? Where do we spend less money? So here we spend more money on vehicles and then in the latter years we spend less money on vehicles than in the baseline scenario, but we spend more money on the electricity generation because we have also cost externalities. So that's our way of doing that. We can also change scenarios. So as I just if you just use storage, the only differences we really have is that our vehicles, for some reason, becomes quite a lot cheaper than our baseline. It probably does. Sorry.
Yeah, I was going to ask. Did you factor in the lending costs maybe for your storage? Maybe that's why.
I think what happened here is actually that we're importing oil. And oil is expensive, and we are going towards BEVs in our policies. So that means we are producing it from cheap electricity here instead. That I think what's happening here. For learning cost, you would put that directly in. I haven't actually looked at the. We could just look at the prices that we input for the transmission, generation processes, energy storage, and that you can see we just put in the capital cost, so that does get quite a lot cheaper. It's just a linear progression. And O&M costs, that also becomes from 37 to 15, so per megawatt production capacity, that goes to about half. And then the variable O&M cost is 0, which kind of makes sense because it does account for losses.
So the decrease in both the capital and the O&M cost, fixed O&M cost, is it as a result of what, of inflation, or is it? It's not necessarily lending, is it?
No, we are working with fixed year costs. So it's in this case the cost is defined as. That's a good question. Monetary year. So this is all in 2019 dollars, and that means this is a learning. This is just things getting cheaper because we get smarter, basically, or the price fall. So this is real cost price fall.
So okay, so we can more or less say it's inflation or deflation related, something like that.
No, so there's no inflation in the model right now. What I put in, so we don't account for that because everything is defined in 2019 dollars, which makes everything nice and easy, or 2019 monetary unit. But what I say instead is, so if a price is decreasing, that just means things get cheaper. Straight up.
Okay.
So that's what's happening here. It's a forecast for saying batteries will get cheaper in the future. Basically, I think this energy storage that they're using is basically batteries.
All right. Okay. Yeah, the question that I was asking about fuel switching is obviously for our case in South Africa, this is what we are getting confronted with because we're realizing as we're doing, these plans. Especially into the future, especially with a higher level of penetration of renewable energy, like wind and PV. So you find out that you need gas to back up, but then we don't have
Maybe.
gas in South Africa. Yeah, so we don't have
Right.
gas in South Africa, and storage prices that we're seeing are still high. So, so what then happens is you need to bring in gas as an import, but then the volumes that are required to make it sustainable are quite high, or could be quite high. So you could then be confronted with having to find another market, you know, other than electricity generation. One of the possibilities is that you could move some of the demand from electricity, like I say, space heating and cooking, say, maybe to using directly gas or something like that, you know? Yeah.
Right. So that's something you could do, yes. The other things you could do, I would suggest looking into DSM, demand side management, because then you can shape your demand, some of your demands more towards what you need in for your what's that called, for your intermittent production if you're using solar and wind, for instance. So then you would reduce your need on gas. I think this is one of those great things that you can do with optimization. Find some good projections on battery cost, DSM cost. If you have some hydro capability that hasn't been utilized yet, like some potentials, put in their cost and their parameters, and then use do a few scenarios like a baseline where you have everything as you have now with your different, preferably where you have, you know, their different load shapes as well. So this is the load shape for air conditioning, for instance, and where you put these things in and then test it with different fuels, like have a very gas demand fuel, with gas scenario, and then have one that's fully electrified, and then where you put in your potential targets and pricing for your for all your technologies and also the one you have currently, and then just let the model optimize, because maybe you will see that yes, you need gas for a certain number of time, and then suddenly you hit a break point in a certain year for something like storage or DSM, where it becomes profitable to do that compared to import of gas. And then it will just change your entire system, and you can't tell by just doing normal math on that, because it's something that happens hour by hour. So suddenly it will say, okay, you have this expensive important gas, and then in 2031 will change, and it will suddenly make sense to do a high investments in storage plus wind plus solar plus some DSM plus something if you have a bunch of gas cooking. And that's something that only the model can tell you when it's working on your profiles, because you have no chance of gaining that knowledge by yourself. Basically, you have to optimize to do that. So that's a really good showcase what this optimization in Leap is really powerful at. Did that make sense?
Yeah,
Yes, thank you very much.
This the lordship, is that the same for all years? We select all years.
Yeah, yes.
I think
Except that so it's percentage of annual load. I can just show you. Sorry, I'm just going to put the yearly shapes up. So it is percentage of annual load. So that means the shape is always the same, but how big it is, I mean, the demand that follows the shape changes over time. So you can say, yeah, so this is air conditioning. You say, okay, in summer, an air conditioning shape looks like this. But if nobody has air conditioning in your country now, then it's still zero. And then as air conditioning demand grows, then you will still have the same kind of shape, but it will just become bigger and bigger and bigger. You can also say percentage of peak, and then you have a more peaky, in absolute number, it would look more peaky than it did before, because it's like it's a multiplication thing you could do. So you can do both of those. So it will be roughly the same shape, but it does grow over time. But I think also that I actually think that's kind of realistic, because what you're doing with your air conditioning is not really it's not so much your what do you call that? It's not so much your your energy demand you're looking into here is your service demand. So how much will people use their air conditioning? Because if you put energy efficiency on it, well, that it will just lower the curve as well. What you can do if you have two pretty fundamentally different generations of a technology, or two very different what do you call that, profiles of your technology, is that in two different scenarios you could put in two different curves. So let's say you've suddenly had an air condition that became more efficient as the more you used it, so, because the efficiency at its peak is the best, for instance. Then you could make another curve that kind of flattens out, so it wouldn't be quite as peaky as this one, so it would flatten out more. And then I would put that into another scenario and try to test that and say, and then put maybe also a price difference in and say, what would this do to our system if we had this policy? That is one of those things that are really, really cool to test. We have done that a bunch with something like heating. So in Denmark, so here we have a heating demand, but even with this heating demand, this is the service demand. This is, even if you have a bunch of technologies that are different, this is the same kind of service demand. But if you have something like a really good geothermal heat pump where you have really high efficiency, it will still have to produce this much, but the energy consumption to do that is just so much lower than, for instance, an electric boiler or natural gas boilers that has lower efficiencies. So this is more representative of the need for the service than the actual energy use. So I think it's okay. That was my very long explanation of that.
Okay. And what's for, you divide your seasons into 4, and the first one is fall.
So in this model,
what's fall by me?
Yeah, so it's here in time slices. If you say setup and set details, then you can configure what kind of time slices you might have. So here I just have 4 seasons and no daily details. I could also have differences between weekdays and weekends, and even individual days, Monday, Tuesday, Wednesday, so on. And then I can have that in this case, it's 24 hours, but I could also have just 4 hours per day, and so on. And then you will get to your total. Of course, the more higher you set your number of hours, in this case, it's a higher number of time slices. In this case, it's 96. Well, the more you have, the longer it will take to calculate. If, for instance, you don't have 4 seasons, so 4 seasons is a very maybe Nordic thing to have, or American thing. We have very big differences between summer, winter, spring, and fall. You may only just have 2 seasons, really, like wet and dry season. Then you should just choose wet and dry season, and then maybe you could go into more details in terms of weekdays and weekend days, where we say take the same number of calculations. The maximum we could do is just every single hour in the year, but I generally don't recommend it because it takes a very long time to calculate. That would take a full 24 hours to calculate if Leap doesn't crash at that time. I'm not going to change anything here to show you, because then the model would try to recalculate, and that would take a long time. So, but you can configure this yourself depending on what you need. I just took a model that someone else had made already with 4 seasons, because it fit the times, the yearly shapes that I already have. It should also be said, if you have decided on some time slices, like here, let's say you actually want 4 seasons and with 24 hours in each, that's cool. If you then say, I'm going to add my yearly shapes, you can actually, if you click on add, click on import, import from time slice shapes. That means it fits the general format we have here already, that fits our timeline. But you can also import from hourly shape, and then you just have a consumption from hour 1, I mean 1st of January, to hour 8,760. So the last hour in the 31st of December, and then the model will actually kind of take care of the rest, or Leap will take care of the rest to make it into these shapes. So if you have all hours, but you want to put them into time slices, Leap can actually do that for you, which is very cool. So in a very short conclusion to a very long answer, choose the time slices you think is appropriate for the results that you want and the system that you have in terms of season, days, if there's a really big daily variation and so on. And then calculate from that. And then you can and then set up your import or make your yearly shapes to fit that time slice, either by importing all the hours if you have that, or making one already that is time slice based, which you can do in Leap or in Excel and then put in here. In terms of also time slices and yearly shapes, I see there's a slight issue in Leap in terms of special cases with holidays. So for instance, our lighting and heating demand is quite a lot higher in a place like Denmark during Christmas. And I know the electricity demand falls rapidly during Ramadan in a place like Indonesia, because the numbers are quite interesting to look at. And Leap doesn't really account for that. So if you want to account for that, you would have to go to a really high time slices, or you may have to do a change your model afterwards to make a special Ramadan case or a special Christmas case or a special summer vacation case, for instance, if that's applicable to your system. So that's just a heads up, but usually these things are not peak hours anyway, so it's not the worst in terms of energy consumption. Did that make sense?
Sure.
Okay, any more questions?
And Mr. Larsen?
Yes.
How this Leap analyze this optimization process? Is that from the inputs we already filled and learn itself in some artificial way, or?
No, it's not artificial. It's basically calculating a bunch of times for each hour to finding out the optimal results. It's not it also depends a little bit on the solver. It is not artificial intelligence. It's a simple thing. It's a mathematical model method called optimization. So it basically means that it finds out for each hour in your time slice, or each of your time slices, it finds out its constraints, like how much energy do we need, what's the constraint you have in terms of emissions for this specific hour, and then it tries to calculate and say, okay, how much of each can we put in, and then it calculates and keeps calculating until it finds a really good answer, or the best answer it can find, to say like, okay, so this is the things we can put in for this hour that has the minimum cost. That's what's called least cost optimization in this case. And then it says, okay, and that's my result for this hour, and then it goes to the next hour. It's pretty complex in terms of computational and requires quite a lot of CPU power in general, but that's what it does.
So it's always lots of probabilistic function segments.
It's not probabilistic. It is not in this case. I don't think they use anything probabilistic, because probabilistic means random, and some optimization.
Gregers, we've lost your sound again. We can't hear you.
Can you hear me now?
Yes, yes.
Yes, we can. Thank you.
Yeah, my headset is weird sometimes. But yeah, but it
So
basically recalculates the same hour over and over again until it gets the right result. That's what optimization does.
okay, so you're saying it does not take the stochastic, it hasn't got a stochastic analysis in it,
No.
like for things like your wind, your renewable energy generation, or even the forecast, for example. No.
Yeah, no, it does not do that. I think you can slightly force some kind of. I don't think you can force a stochastic on it, but I expect that you can make some things random that is not random right now. If you see the results on the power generation, you can also see that the wind production is way too stable. Like it's over all these hours in a spring day, it's exactly the same wind output. And that's just something that Leap says, okay, that fits somewhat because it's a thing. But if you were to do, generally for long-term energy planning, the precision of our hours, of course, is like calculating an hour in 2040 doesn't really make sense in terms of if you want something very specific and randomized and stochastic. It's only if you want to invest in your right specifically right capacity of something like transmission lines, you really need to be careful about it. And then we use stochastic modeling, but we do that with other models. Here
Okay.
we're trying to get ourselves a grander overview to know what we have to invest in. And then this is seen as quite enough. That's also why we have a fixed reserve margin. It is if we use this to invest in a bunch of wind, and then on our certain hours we have more demand, less production with wind, we always have 30% on top of power of dispatchable production that's been that we already have accounted for in terms of cost that we then can put into our model, even though that would not be the quote unquote normal situation.
Okay, I understand. Thanks. And then one last thing from me. I know I keep on saying one last thing, but how do you account for? I suppose like your wind is not necessarily on one site. If you have different sites where your wind farms are you able to take into account of that variability, so to speak? Because different sites will have different wind patterns, so to speak.
Not in a hour by hourly basis, but if one wind farm is better than the other, like let's say you have an offshore and an onshore wind farm that could be technically the same capacity, for instance, but the wind resources is better offshore than onshore, then I would just make two technologies that are both wind, both renewable, slightly different parameters, might also have slightly different cost. You're free to do that. That's the easiest way of doing that. In terms of, and then your full load hours would be different, and that would be the main factor. And then you would also see them as two different technologies when you are in your results, and you can see specifically, okay, we are going to use more the offshore than the onshore, or vice versa. So yeah, you can do that.
And then you would be providing for those two technologies that you've done. You'll be then providing Leap with a profile, right? Am I correct? That you will then
yes.
Or do you just provide? Oh, sorry. Do you just provide a capacity factor for both?
So in this case, what they chose to do is for just wind, they just gave a capacity factor, but for solar, I just need to find it. Sorry. So here if you have just oh, that's full hours. That's my bad. That was not the right thing. Here you go. So here they just have a seasonal grouping for wind and hydro with basically the capacity factor actually in there. That's a way to do that. But with solar PV, you can see that did a yearly shape, solar V2, and that's a shape that we have in our yearly shapes up here. That's hello Leap. That defines how much we produce with our solar in each season. So you can actually do both. The only thing about the the wind, why they haven't done that is because it's a little too intermittent. So they just take these weirdly average values, so it's just flat, because wind doesn't adhere, in most cases, doesn't adhere to a specific profile like solar. Like you can always tell when there's most sun, that's at noon mostly in the summer, but wind can be up and down. So therefore they simplified this quite a lot.
Okay. All right. Yeah. Yeah. It's unbelievable. Like I think it's amazing. Rather, I mean, so things like ensuring that you don't have too much of it, like the wind, for example, because you're using the capacity factor over the peak hours, for example, so that then you end up underbuilding. And then on the solar, I think if you use the profile like that, then I'm assuming that it takes into account of the cloud cover, things like cloud cover and stuff like that.
You would do that in, it doesn't change based on cloud cover, but you can do that in your profile itself, like have an average. Some things in Leap are somewhat simplified. If you wanted it to act that randomization, bigger models will do that, and they would do that on the hours as well. So something like a Balmoral model that DA also uses, that it actually does that. But again, computationally, it's a little harder, so that's why it uses a server usually. And it's just a general bigger model that runs on a CPlex solver, which is one of the most efficient solvers as well, just to be able to do kind of these things. Leap is a smaller software, and sometimes you can feel that with these kind of things, but that happens.
Okay, so your comment, sorry, I don't want to, if other colleagues on the platform wants to talk, is fine. I don't want to monopolize the stage. But I think you made a comment, a colleague here on this platform asked about whether you'd use Leap for optimization or another software, and you gave a response that maybe it might be better, depending on what you're solving, to use other softwares like Balmoral and stuff like that for optimization in particular. So these things that you're mentioning are some of the considerations for that decision, or that recommendation you made, I'm assuming.
And also one big major decision is we don't have geography normally in Leap, and especially not with optimization. So if, let's say, I invest heavily in just one nuclear power plant or a bunch of wind, it does not necessarily take well into account the new number of transmission lines that I would need, or the new number of distribution lines that come with like these major decisions. Like you could even see a country making a policy of building something demand side, like industries close to a wind source or a nuclear power plant, or building close to the offshore wind turbines, like we see some places. Leap cannot take that into account because it will not optimize the transportation of electricity. But Balmoral does, and therefore I would use Balmoral to some of these things. If you're doing something regional, like a smaller region where you have some imports and exports to the rest of the country from the region, and you don't have too many production units of electricity and so on, I think Leap can do a great job, really. But there's a really strict boundary to it.
Okay, I understand. Thank you. Thank you very much.
And of course, then the other thing is, it depends on also how accurate do you want it to be, because if you're sitting and testing some pretty big policies, like for instance, the importing a bunch of gas for cooking or to use in power plants, that kind of scenario I would run first in Leap, because actually making that scenario in Leap compared to making that scenario in Times or Leap plus Balmoral to get the same result would be way longer. It would take, in terms of man hours, way longer to do that. So I would test that out in Leap first, and then say, I might be missing something. It might overestimate some of the prices a little bit, some places. But if there's a huge difference between the two, then you already know which direction you might want to take to a bigger model that cost more to run. So
Okay.
pre-feasibility, so to speak.
Okay, I see. All right.
Any more questions? Feel free. This is also our last Q&A. So if you have questions to any of the lessons or any of the stuff that you didn't quite understand, or any comments, I understand I'm a bit late up with videos. I know that. That's entirely my fault, and I apologize. I will leave them unlisted until now, and hopefully they will be on Leap's official YouTube, is the arrangement, and they will be fully public in not too long, maybe in a slightly edited version. So you will always be welcome to repeat looking at the lessons. But in terms of Q&A, this is more or less your last chance for this time at least. Or if you send me an email, but that's a different thing.
Okay. And I didn't see, I saw you touched a little bit on the social costs for the different scenarios, but on the optimization for Leap, I didn't see anything about the total objective cost, for example. Maybe where you may want to compare the scenarios in terms of the NPVs and stuff like that.
That's a good question. In terms of NPVs, I mean, we don't have it. So the way that Leap, you can see it on the screen as well, the way that Leap tells you cost of different things in the model, it could do that in different ways. It doesn't really tell NPV. NPV is more of an input in terms of Leap. You can have Leap tell you the discounted cost, which is similar to NPV. So that takes into account an interest rate for the cost in the future. So if you just say no comparison, community cost, discount cost, real cost, you can see that's quite a difference when we get further out where we have our costs. So it can do that with discounted cost, but it's not really NPV. But you can do also absolute values with discounted cost as well. So you can see that's quite a big. This is the interest rate difference. So this is the closest thing. Yeah, so it doesn't really show NPV or objective cost in that manner, but this is the discounted cost for your scenario is probably what your finance ministry would use. So it does give you that.
So you could if you extract these on an annual basis, for example, the different cost categories, then you can calculate your own NPV costs on a spreadsheet or something like that.
Yeah, exactly.
Okay. Can you also show like on a year by year the different cost splits, like O&M, variable capital, and all of that?
Yes, I think so. So here we have cost of production. I'm pretty sure this is just now I'm getting a little. I'm not quite sure if this is just O&M cost, but I think this is O&M, variable O&M, fixed O&M, and fuel. On our different of our different technologies with the capacity that we have. And then we also have investment cost. So this is the investment cost per year. So you can see this is our big investment year where we're retiring nuclear and investing in something else. There we have a bunch of investment costs. So you can split those in Leap without having to look further into the data quite well. You can also define an electricity price, which here is not great. So you can also see what your revenue is or your profit is for your electricity sector. I'm pretty sure here is more or less defined as zero cost, so it doesn't really give a true result here because it doesn't. It's not balancing out. So this is just our cost in minus. But if you give it you can give electricity a cost per unit, so a sales price more or less. And then you can tell it, then it will also tell you how much money is the revenue or the profit margin for your generation plants, individual plants, which is also quite cool. Then you can also that can help you decide on fair electricity price as well.
Okay.
Yeah, because sales revenue, there's no cost for the electricity. That's why we don't have sales revenue. Exactly. But you can see that too for the different things.
Okay.
Any other good questions? You are all welcome.
Yeah, I want to ask a question.
Yes, of course.
Yes, if I want to assign a battery only for, let's say I only use batteries for solar, I leave wind intermittent without any batteries or auxiliary services. Can I do that in Leap?
I don't think so. So you're probably thinking about on-site energy storage with solar PVs, right?
Yes.
Yeah. Not really. It's again, it doesn't aggregate in terms of geography, unfortunately. I will say this: if you it will benefit that, but on the other hand, if you are doing like one of those like huge Tesla batteries that they put next to wind power plants, that is mostly done out of sheer what do you call that, convenience in terms of power lines. So you have lesser losses from the wind going into the battery and so on, that we also don't really define here. So I think it's fair to define it for your entire system. If your system, unless your system is too big, if you're taking the entirety of your country and then put energy storage, it will be a little bit difficult. But if it's a more localized system, you can say it for the entire system. Because also, if you do have an unbalance due to your big power plants, that its production is just a little higher than the demand, then it also will flow into the batteries as well in a real system as well. But if you have a small system, it will probably also benefit the solar. But that being said, because of the profiles of solar, I can almost tell you already it will still base itself on your intermittent resources as well, because that's what it will try to balance out anyway.
Okay, thank you.
Yeah, in short, the answer is no, but it doesn't really. I don't think it's a big problem. I think it's you can still input different energy storages. It should also be noted that in the model that I used, of course, we just put in energy storage, but just like you have multiple wind farms and multiple solar PVs with different parameters, you can do the same thing with energy storage. So you could have one that's called batteries and one that's called pumped hydro, CIES, and so on, and you could just dump them all in there with however your technology possibilities are in your country, and then they can also decide between the investments and capacity additions of your different energy storages. So you may think you need to invest $1 billion into a big pumped hydro plant, but if you put that in and also put fair pricing for lithium ion and so on, then you might even find that you may not need to invest in that. You can just invest in a small amount of lithium ion instead, just to balance out your intermittent resources. It's one of those things that only optimization can really tell you.
Do they have costing for the energy storage? I don't think you showed that.
Yes, we do have that. So here in the energy storage, we have to be in current accounts, I think. We can say we have a capital cost. So here's per megawatt, and fixed O&M costs. And we also have some, we also have some variable O&M costs somewhere. Oh, no, wait. I'm not sure, because of storage, it might actually have a variable O&M. So variable O&M is there. Oh, we do. I just couldn't find it. They just set it as 0, which is also kind of fair. So yeah, it does have costing. So it's in the model that I showed you, where it has a bunch of energy storage, that is not done with exogenous capacity, meaning that we force it to invest in that, or it's already there. That's what it thought was worth investing in, because we don't define that it should have any energy storage. It just decides for itself. So in this case, we said, oh, you don't need to invest in it. Yeah, or you don't need to have it, only if you think it's fine. And then here in optimized new capacity for energy storage, we can sell by 2040 in this scenario. We have 2.2 thousand megawatts. So that's 2.2 gigawatts of storage.
Okay.
So quite a lot. Yes. Any other questions? Any questions to the general exercises before I give it to you?
Okay, Mr. Larsen.
Yes.
When I try to see the results, there is some warning on this time slice. It says
This one?
Yeah.
Okay, so this is just tell you so if you have some diagnostic method, that means your model still works, but Leap thinks that something is weird. So it's really nice. This can be done by a lot of things in Leap. So I'm just gonna click. You can click yes, and it will show you right away. But now I'm just gonna click no, so I can tell you where it is. So up here where you have charts, table, split, that shows both. We also have one that's called diagnostics, and this one, if I'm in demand or if I'm in anywhere else, it's the same thing. So here, we can say the process energy storage scenario expression set to 0 when a parent scenario was non-zero. So somewhere we probably set the current accounts to have some energy storage, and then baseline to not have it. And that's Leaf saying that's kind of strange when you're, when you have inheritance, it's usually you have a standard and then you change something. So here we change something by already having something and then removing it, which is strange. And that's just Leap telling you that. I didn't do this, so I don't know why that was done, but it's just what it's telling us. So if we double click on this, it will go here, and you can see here in pole 1, it's not always good at this. So in current accounts, I just need to check something. This is not where it's from 0. Sometimes it doesn't show you quite the right place. It should be exogenous capacity. No, I don't know what it is. But there is somewhere here in one of these variables where the baseline has something that the current accounts has something that the baseline does not, and that's just what it's warning me against. Here it doesn't mean anything, but I don't know. I don't know why, to be honest. But that's something you can start looking for. Leap is not. It's nice that it shows you, but it's not good at showing you completely what it is wrong. But you will see this a lot when you start working with your own model.
Okay.
It generally means you probably have to check something, but it doesn't break the model. Any other questions?
And Mr. Larsen, is that not possible to calculate load forecast, demand forecast using Leap?
Not
just
yes.
From the trend data, we have trained consumption data. Then by feeding those trained data, we want to know our demand just a projection for some specific year. Is that possible?
Yeah, sure. But not optimization. It doesn't do optimization, but we still calculate it.
Yeah,
do
not
it continuously.
optimization.
Yeah. So if we go up here into our branches in demand, and I'm now just social cost, I'm going to put here in demand instead. So here is, for instance, is my energy demand in final units in my branches. I can also just choose my fuels. I will just do that. So this is my, on my demand side. So this does not count the coal I'm using for a power plant and these kind of things. But for my demand side, you can see I'm using quite a lot of gasoline, but it's decreasing in this scenario, and I'm using quite a lot of electricity, which is probably increasing. And a little bit of direct natural gas. This is probably cooking or heating. So that we can have tell us, and quite a lot of other things too. We can also tell us the useful energy demand, which is the service demand. So efficiency is getting better. That's what we can actually see from the difference between two. And then we can also see these primary requirements allocated to demands. Interesting. So so the reason why it's weird right here, that's because again we are retiring nuclear and investing a lot in other sources. But basically what we're saying here's all the different energy sources we need, including transmissions. So this is all the different primary and secondary fuels we need, but also electricity is also in here. I think this must be, I need to check something, gasoline, solar, no? Wind, okay. So this must be imported electricity because it's just given it to us directly as electricity. So we do have some electricity imports here. That must be. We can also check that real quickly. Resources, imports. No, I was wrong. There's only natural gas and wood import apparently. And in terms of exports, nothing. Oh wait, no, so we're exporting electricity. I don't know why the demand of the primary requirements also says electricity. That's worth digging into. I don't know why that happens, to be honest. Sometimes leap results are a little weird. It probably makes sense. I just can't see it right now. But you can find a lot of also the different demands. So even if you have optimization and you have a lot of land type use and all these other things, that only adds to the results you can see. You can always see some results for your demand and your resource use and all these things. And also you can see how your reserves are doing. So we're gaining reserves. That's kind of cool. It's probably not filled out that well. That's why. We can also see our primary supply, which here is just natural gas and wood for some reason. That's kind of strange. And we can also see our degree. No, okay, we don't have it here. I think because we don't have we don't really have imports and exports, so we can't see our degree of self-sufficiency. But normally you can also see that. Of course, that depends on what you have in your model. Unmet requirements, we do have some for nuclear. That is very interesting. That I would look more into. That's no, sorry, that's just indigenous production. No. So that's fine. So this is a production from our nuclear. It won't tell me the unmet requirements. That usually means that's 0. It sometimes is a little weird. Also, what should be at? Again, sometimes leave is a little weird. Okay. Again, yeah, but that's you can also see our social cost between scenarios. That could probably be interesting. So this is our social cost in discounted values for our different scenarios. So see you can also see cumulative probably please. Yes. So actually, the cheapest one it says here is the policies scenario, and the policies with emission constraints. And the most expensive one is our baseline, so that we can judge in terms of cumulative social cost too. Sorry, that was a long answer. Did that satisfy?
Yeah, sure.
I think when you have made your model, if you're making your own real model, you should also have spent quite a lot of times in disseminating and looking into your results. One tip for that, if you're looking at something and you're not quite sure what it is, especially in result, this little question mark, that will bring you right into the guide, what it means, and what the different categories are and so on. So you can see here we have different forms of cost categories. So we can also say, what's our environmental externalities between the different models, only that, or the fuel import, all zero, that was nice, or the transformation capital. You can see the policies with externalities is higher in that in cumulative cost, and so on. So that's something we can also look at, especially if you look at something like fuel imports and maybe fuel production. Those are generally quite important. Any more questions? All right. Should we end it here? It is also 11:50, so I think you also need to go back to your day jobs if you don't, if you have no more questions. And then by tomorrow evening, I will have sent out an email to all of you and put on SharePoint exercises, both as a video, and I think also just put up the PowerPoint without the video, so you can also look at the exercises easier in what I've written down. Is that understood and okay and with everybody?
Okay. No,
Yeah.
do we have a lesson on Friday also?
No, this was the last lesson.
Oh, okay. So no lessons on Friday.
No, I will probably put out a after you have on the 20th when your LEAP license ends. On the 19th, I will put out a short video lesson talking about results from the exercises.
Okay.
Yeah, hello, can I ask you, please?
Yes.
Yeah, sorry, yeah, in our Tuesday meeting, I couldn't join the class, the online class due to some other overlapping class, and I missed your presentation, so I hope you have the recorded one. So can you please?
Yeah, I don't have that for the Q&A, but for the lesson 2 that was on Tuesday.
Yes.
That is on YouTube, and it is right.
What about the lesson 3 you don't have?
For lesson 3, we have the everything. Just a second. I am just gonna go here. So for all of you as well. Sorry, I need to find that. Everyone meeting. So I'm gonna send you a link. This is the playlist for the lesson 3, including the Q&A, which is on YouTube.
Okay, thank you. Thank you very much.
Welcome. Anything else? All right. I will see you guys. Good luck with the exercises. Whoa, over here. Bye. Bye.
Thank you. Bye-bye.
Don't make it too hard.
Thank you.
I'll make it very hard. No, I think it should be. I will make it appropriately hard or easy.
Okay, thank you.
All right. See you.
Bye.
See you.
Bye.
Okay, bye.
Bye.